All right, in this video I'm going to be working some problems that have to do with span and null space and range of a matrix. Okay, so let's see. These first ones are talking about compute the span of a set, where they're going to just kind of give you the vectors over here. Maybe I'll get it all set up like that. And so we're going to compute the span of the set that has W and V in it. Okay. So I'm going to take W and V and put them together into a matrix. I'm going to augment it with B1, B2, B3, and I'm going to row reduce and see what kind of vectors can I get back. Okay, so I'm going to subtract 2 of row 1 from row 2. So that'll be B2 minus 2 B1s. Then I'll have 0, 1, and that'll just be V3. Okay, what this is telling me is that if this is going to be consistent, if I'm going to have any outputs at all, then this needs to be the negative of that. Okay, so I'm going to go ahead and kind of keep pushing on that front. Okay, so I can tell that I'm going to end up with something that means like B3 equals the negative of B2 minus 2B1. Okay, but I'm going to show you how that happens in the row reduction. 1, 0, 0, 0, 1, 1, B1, 2B1 minus B2, because I just multiplied by a negative 1, and then B3. All right, I'm going to take this row minus that row, and I'll be left with 0, 0, 1, 0, 0. That's not a 4, it's 1. And, okay, on my 0 row, I had 2B1 minus B2, and I'm subtracting B3. And, well, what I'm basically saying is that that has to equal 0, right? But that's exactly what we're saying here, the exact same thing. And so while, you know, these numbers here, that x1 equals b1 and x2 equals 2b1 minus b2, well, that's something we might use later on in like number 5 or something. Number 2 is v, x, and y. So I'll take v and x and y and put them together into a matrix, row reduce it, and be happy. Okay. So v is 1, 2, 0. X is 1, 1, negative 1. And y is negative 2, negative 2, 2. Oh, okay. I can see right now that, you know, the second column is negative half of the third column. So looks like this is going to have a limited span. It's not going to span all of R3. I can guarantee that. Okay, so the span of this, I don't know what it's not really equal to. Let's see. Pardon me. All right, I'm going to row reduce this thing, and I'm going to subtract 2 row 1s from row 2. 2 row 1s, so 1 minus 2 is negative 1. Right, then I have subtracting 2, negative 2 plus 4 is positive 2. I didn't change anything down here. This is B2 minus 2B1. And, well, this is just B3. So what I'm going to say is that B3 has to equal B2 minus 2B1. I'm just realizing that I did not actually finish the first one. Yeah, I didn't actually give a specification. Yeah. Okay, well, that's why y'all are in here. You're supposed to be like stopping me before I do something silly like that.
Yeah, so I just always assume that I'm stupid. So
okay, yeah. No, you got to stop me. But at least I realize now. Okay, so what I'm going to do, I'm going to say that in order for this to be consistent, I need B3 to equal B2 minus 2 times B1. Okay, this is number 2. And so my span is equal to the set of all 3-dimensional vectors for which the third component is equal to the second component minus 2 of the first component. But if you wanted to call the set of all b's so that b3 equals b2 minus 2b1, that's the exact same thing, right? Algebraically. It's kind of like, in calculus when we were integrating, the integral from 0 to 1 of x squared dx is the same as the integral from 0 to 1 of t squared dt. Doesn't really matter, right? Oh, that's the actual homework set. I'm going back up to correct my earlier error on number 1 and give you a coherent solution. I'm going to actually just grab a little scrap of paper here. And all right, here we go. Back to number 1. So I've got b3 equals negative of b2 minus 2b1. Okay? But that's what I was saying. Also, this needs to equal 0 in order for this not to be inconsistent. So I'm going to say 2b1 minus b2 minus b3 equals 0. Well, maybe I'll say that's equal to b3, like we were saying. Okay, so the span of that set that I was originally trying to find is the set of all, maybe I'll just call them b's right now. B's for which b3 equals 2b1 minus b2. And just something I might want to throw out there is that this is like in 3-dimensional space, the plane z equals 2x minus y. Okay, just gonna throw that out there. All right, moving on. Number 3. Okay, S is v, w, and x. Okay, so v, w, and x, that, I don't know. We'll find out. All right, so I've got my matrix copied down. I'm going to row reduce and figure out what the span of the set of these 3 columns is. So I'm going to go and subtract 2 copies of row 1 from row 2. So, right, yeah. 2 copies of row 1 from row 2. So I'll have 1, 0, 0, 0, negative 1, 1, 1. All right, if I take 1 and I subtract 2 1s, I'll have a negative 1. And that's still that. All right. So, are we sure about that? Yeah, okay. b2 minus 2b1. Yeah, subtracted 2 row 1s. And then on row 3, what did I do? Doesn't look like I did anything. So that's still b3. And now I'm going to, maybe I'll add there. So okay. What did I do here? Yeah, that's unchanged. That's B1. Okay. Now, at this point, I know that I'm going to be able, I can see, I'm not sure if you can see it at this point, but at this point, I can see that I'm going to be able to divide this by negative 2, use that to clear out the rest of that column, and I will have a unique answer in terms of B1, B2, and B3 for all 3 slots. Which means to me that, the range is going to be all of R3. But maybe I'll actually go through and show you the rest of the steps and see how can we actually see that. Okay, so I'm going to divide by negative 2, which I'm not super excited about. I think what I'm going to do, turn that into a 1, divide that by negative 2, right? And so now I can take that and subtract it from B1. So really, I'm not going to have enough room. I'm going to have to say 1, 0, 0. All right, I had B1, and now I'm subtracting. Really, I guess I'm going to subtract that thing divided by negative 2, so I'm going to add that divided by 2. And then this is that bad fraction. Divide by -2, b2 minus 2, b1 plus b3. And then over here, just b3. But what this is saying is that if you give me any b1, b2, b3, then I can figure out a combination of the columns of the original matrix all the way back up here that'll get you that vector b1, b2, b3. Okay? So I'm going to say that the span of that set S is all of R3, because there's nothing that can't happen here. You can choose any b1, b2, and b3 and work your way back to a combination of the columns of the original. Okay, number 4 is W, X, and Z, so all right, I'm not sure how that's going to play out. W, X, and Z. Okay, what I'm going to do, I'm going to use this one as the first column because it's going to work out the same way. 1, 0, 2, W, X, Z. So I'll take that one, 0, negative 1, 1. And then X is 1, 1, negative 1. Whoops. Now I'm going to reduce. All right. Subtract 2 row 1s from row 3. I might also make that a positive 1 and a negative 1. Call that negative B2. Okay, if I subtract 2 zeros here, that would still be 1. If I subtract 2, that will be negative 3. Right, did I not already do this one? VWX, WX, okay. Evidently not. So then this is still B1. Right, now I'm going to subtract row 3 minus row 2. Negative 3 minus negative 1 would be negative 2. If I subtracted row 2, I am adding B2 minus 2B1. And now I can see what's going to happen is I'm going to be able to divide by negative 2, clear out the rest of that column, and then I'll have a, for any B1, B2, B3, I'll have a unique solution, meaning the span of that set is all of R3. Okay, for number 5, we already did this. This was the first problem. We computed the span of V and W. So I'm going to just kind of bring that back since I had kind of copied it there. And for each of these, I'm going to just test that point against this set of conditions. Okay. Now, what a person could do if they hadn't already computed this, we've done this all throughout the course, is we could augment. We could basically solve the system how many of V plus how many of W equals this vector by taking V and W, putting them together into a matrix, augmenting with this, row reducing, and that would give us a solution. But just to be a little faster, I'm going to get that over here. Say we're saying Z is 2x minus y. So is Z equal to 2x minus y? A is yes. Okay. And I'll come back to express it as a combination of V and W in a little bit. B is 2x minus y equal to negative, no, 2 minus 1 is not negative 1. Okay. 1, 2, 0, 2x minus y equals 0, yes. 2x minus y equals 1, yes. Okay, E and F, okay, I didn't budget quite enough. Okay, E, 2x minus y, no. Okay, so B is no, E is no. F, let's look at F. 2x minus y equals z. No, I don't think that one is either. 2x is negative 2 minus 2 is negative 4. If that had been negative 4, it would have worked. Maybe I copied the problem wrong. Anyway, I think 3 is going to be enough for us. B, E, F also is a no. Okay. Now, I'm going to have to go dig up the matrix that I was working on for number 1. Yes. Okay. So I'm just going to kind of copy it over here in red. I'll bring that sheet back when I need it. So I'm going to copy down kind of my last matrix that I was doing when I was row reducing in red. One, 0, 0. Zero ones, pardon me. I was looking at the wrong matrix here. All right. Now, at this juncture, I'm interested in, how many V's and how many W's do I need to take to get, A, for instance. But that's these numbers here, like x1 and x2, the numbers of each of the columns I have to take to get, v1, v2, v3. Right. So what I'm going to do is I'm going to say that, okay, maybe I'm going to need some better terminology here to, better solve this problem. I'm going to call this one A, this one B, and I'm just going to call them all by their letter. Okay. And I'll be interested in solving, like, for instance, for part A, how many, K1 V's plus how many K2 W's does it take to equal A? But this is giving me information about K1 equals B1. K2 is 2B1 minus B2. Okay. Evidently, we don't really care about what happens to B3, except that it has to fit that pattern in the first place. Okay. So when I'm going over here, I'm going to say A is 1, 1, negative 1. Which means that in this situation, B1 equals 1, B2 equals 1, and B3 equals negative 1. So the K1 equals B1. That's equal to 1. K2 equals 2B1 minus B2, which is a 1. Okay, so that's 2 minus 1, which is 1. So if I take 1 V and 1 W and add them together, which I'm going to have to scroll back up a little bit, do I get 1, 1, 1? Yes, I do. Okay, cool. And I'll move a little faster through the next ones. I have to, okay, B was a no, but C is a yes. So I just need to do C, D, and just C and D, I guess. Okay, whatever. So for C and D, I'm interested in expressing 1, 2, 0 as some number of V's plus some other number of W's. But I've already done all the row reduction, so in this situation, B1 is 1, B2 is 2, and B3 is 0. And, okay, so K1 is equal to B1 is 1. K2 is 2B1 minus B2. That's equal to 0. 1, 2, 0. Oh, yeah. 1 V, no W's. Go up here and look at, oh, that's V. I feel like that's obvious. Okay, anyway, it's all right. All right, so D is evidently also a yes. That's 2, 3, 1. So we want to find out 2, 3, 1 equals some number of V's plus some other number of W's. Okay. Since, using kind of my cheat sheet over here, K1 is equal to B1. So I'm thinking K1 equals 2. And K2 is equal to 2B1. 2 times 2 minus B2 is 3. So that's 4. That's just going to be 1. So evidently 2V's plus W equals 2, 3, 1. Yep, sure enough, 2V's plus W does equal 2, 3, 1. And that's all for number 5. Okay. Now, kind of the more traditional, compute the null space, compute the range. We can do that all day. So, number 6. For number 6, I'm going to say 1, -3, -2, 6. Okay, I'm going to start with the null space, I guess. Okay. So that tells me x1 equals 2x2. And so the null space of A is equal to the set of all x in R2 for which x1 equals 2x2. Maybe I'll say x is equal to x2 times, well, x1 is 2 times x2. So set of all possible multiples of vector 2, 1. And I'll slide over here and do the exact same thing. 1, -2, -3, 6, augmented with B1 and B2. Oh, whoops. I'm going to row reduce. I'm going to get 1, 0, -2, 0, B2 plus 3, B1, and still B1. Okay, that's reduced echelon form as far as I can go. So the range, in order for this to actually have any outputs, not be inconsistent, I need B2 plus 3B1 to equal 0. So the range of A is equal to the set of all vectors x in R2, where B2 plus 3B1 equals 0. That's a perfectly valid way to express that with an equation. Number 7. All right, for null space, I'm going to row reduce this thing. Skipped a couple steps in there, but I can see what's going to happen. I'm going to subtract, then I'm going to subtract up. So I guess I skipped a step. So the null space of this matrix is equal to, well, x1 equals 0, x2 equals 0. That's only the 0 vector. Okay, well, that's easy enough. And now I'm going to 1, 1, 1, 2, B1, B2. All right, now the subtracting up there, I'll have B2, or B1 minus B2 plus another B1 is 2B1 minus B2. But, there's no actual restrictions on these B1 and B2 have to equal anything, right? Because they can really be whatever they want. And I'll be able to solve for, a number of each of the columns. I need to get any point in R2. So what I'm going to say is that the range of this matrix A is all of R2. And what we'll see is that the ones that have a very limited null space has a really big range. And I guess the ones that have a really limited range will have a really big null space. But we might not be seeing that in, it doesn't look like we'll be seeing that example. Maybe number 12 might have a, and therefore a small range. But I don't think as extreme as the one we just did. All right, number 8. I'm going to take 1, 2, -1, -1, 2, augment with 0, 0. Okay. I'm interested in computing. So that'll be subtracting 2, that'll become a 1. Subtract 5 minus 2 2's is 5, yeah, 5 minus 4 is 1. All right. Then I'm going to do one more step, and I'm going to say 1 0 0 1 3 1. So kind of my interpretation is going to be x1 equals negative 3x3. x2 is negative x3. Whoops. So the null space of A is going to be the set of all vectors in R3, it looks like, for which, you know, x equals, okay, x1 is negative 3 of R3, x2 is negative 1 of x3, and x3 can be whatever it wants. So I'm going to say it's all the multiples of negative 3, negative 1, 1. All right, now let's get the range of this thing. So 1, 2, negative 1, 2, 5, 0, 0. And we're going to compute the range by, wait, no, B1, B2. I already computed the null space. So 1, 0, negative 1, 0, 2, 1, B2 minus 2, B1. Then I'm going to, wait, that's going to be the 1. Yeah. Now I'm going to add up. Okay, that's promising because I got the same kind of like reduced echelon form that I got before. But I'll have B1 plus, didn't I already do this problem? It just felt the same. So what I had was, I had a B1, and then I'm subtracting this away, right? No, I'm adding it. So I'm adding negative 2 B1s. It's going to be a negative B1 plus B2. And let's see, then down here I have B2 minus 2 B1s. And hold on just a second. Oh, I see. There's no restrictions on B1 and B2, right? B1 and B2 can be whatever they like. Okay, no matter what you choose B1 and B2 to be, we're going to have a consistent system. We're going to have, you know, a combination of these columns to get you there. Which is not surprising because I have 3 vectors in R2. That collection must be linear dependent, so I can make any vector in R2 out of them. So, or then along with their span being R2. But anyway, the range of A is equal to all of R2. All right, I'm going to start to move a little faster here. Number 9, I'm going to row reduce, and I'll have 1, 0, 2, 0, because I'm subtracting 3, and I'll have a 1. But then I'm going to subtract here. I don't know how that's going to go. I'll put a 0 there. Okay, so that means x1 equals negative 2x2, and x3 equals 0. So my null space is equal to the set of all vectors where x1, x2, x3 is negative 2x2, x2, and 0. All right. And that's my null space. Then over here, to get my range, I'd do the same thing. 1, 0, 2, 0, 1, 1. B2 minus 3 B1s. That's how I did the row reduction. And now what I'm going to do is I'm going to subtract this up there to get rid of that one. So I've got B2 minus 3 B1, and then B1 minus that, so that's 4 B1 minus B2, because I was subtracting, yeah. Okay, again, no matter what B1 and B2 are, I'm going to have some kind of combination of the columns that can make that happen. So I'm going to say that the range of A is equal to all of R2. was number 9. Number 10, I'm going to just copy so the video is not so long. All right, number 10, the row reduction wasn't super exciting, and it was very much like you would expect. So I just did all of it for you, and now I'm going to conclude that the null space of that matrix is just the 0 vector, right? Because that means x1 equals 0, x2 equals 0, and x3 equals 0. Same type of operation. Now, what's going to happen is when I row reduce, I'm going to have all these b's attached. I'm actually not going to do this part, because especially with a square matrix, I think it's easy enough to see. If I augment with just a bunch of b's, and I take all the same row reduction steps, I did not show where I cleared that column back out, but it was pretty easy to clear out the lower half of this triangle. I'm just going to have a bunch of b's hanging around over here. I'm not going to have a row of all zeros, which is going to necessitate some sort of equality, like b1 plus 2b2 minus 3b3 equals 0, or something like that. We aren't going to have that happen. So we know that it's going to row reduce the same way over here, and I'm going to have a unique solution. And so there's a unique solution for each choice of b, means that the system or the equation ax equals b is consistent for any choice of b, meaning that the range of a is equal to all of R3. Okay. Now the fact that these two are complementary, that is something that we're going to be learning about as we move forward in the course, but it's related to the rank nullity theorem. So number 11, all right. Another 3 by 3, and maybe this is going to be a singular matrix. Because those are the ones that are more interesting, especially like 3 by 3s. You want a singular one. Have an interesting null space, interesting range. Otherwise, it's going to be null space, just the 0 vector, and range all of R3. So all right, I'm going to compute the null space of this matrix by starting off and clearing out that that column. 3 minus 2 is 1. 2 minus 2 is 0. That's really convenient. 1 minus 3 is negative 2. And 10 minus 6 is 4. Okay, but we know that all triangular matrices are singular or non-singular, so I'm going to be able to divide this by 4, clear out the rest of the column, use that to clear it out. So I know what's going to happen is 1 0 0 2 1 0 1 0 0 0 1. So again, I'm going to conclude that the null space of this matrix is just the 0 vector, and the range of this matrix is all of R3. I like this one, number 12. This one's interesting because what I'm going to do, I'm going to use this 1 to clear out the 2 and the 3. Okay, and that's all I'm left with, right? That's interesting. So what I'm going to do is I'm going to say, well, the null space of this, all that has to happen is x2 equals 0. x1 can be whatever it wants to be. So I'm going to say that the null space of matrix A is the set of all vectors x for which x is equal to some number times 1, 0. As long as that second component is 0, then I will get 0 back when I multiply A by x. All right, and then for the range, all right. All right, we know how it's going to row reduce. I'm just going to subtract 2 b1s from b2 and 3 row 1s from row 3, so b3 minus 3 b1s. It's still b1. And now I need these two things to both equal 0. But that means that they're both equal to each other. So, yeah, I'm just going to say wait a second, hold on. Right, really not sure where I left off, where I paused last, but I see I'm in the process of finding, this is like an hour later. I see I'm finding the range of this matrix, and I've gotten it down to reduced echelon form, so I know that this needs to equal 0. And that needs to also equal 0. I don't know if I'm going to have enough room to write that. All right, there's my sheet. We'll see. B3 minus 3B1 equals 0. Maybe I'll just say B3 equals 3B1. Okay, and that's fine. So now I'm going to say, okay, B2 equals 2B1. So I've got myself a little pattern here, right? B1 can be whatever it wants. So my output vectors are B equals B1 can be whatever it wants. B2 is 2 times B1, and B3 is 3 times B1. Which means that there's just enough room here. The range of A is equal to the set of all vectors X, which is equal to some number times 1, 2, 3. But if you go back and you look up here, the columns of this matrix, this is just the span of the two columns, right? This adds no span, and that's going to have like a line's worth of span, right? Any given vector sits on a line through the origin, and the span of that vector on its own, or I guess in conjunction with the 0 vector, is just going to be that line, and that's what I'm saying here. Okay, that was number 12. Number 13, one more. I can do this. I'm just get a fresh sheet of paper, though. All right, 13. 1, 2, 1, 3, 7, 5. Let's find the null space first. Okay. Well, subtract. Oh wait, no, gotta go down. 1, 0, 0. We're going to subtract 1s from row 2, so it's going to be 1. So I'm subtracting 6. And then I'm subtracting 1, and so I'll have 2. Okay, I'm going to use that to clear out the rest of the column, and I'm going to get 1, 0, 0, 1, 0, 0, 0. Okay, so that's going to be a 0, and that's going to be a 0. And so I'll say x1 equals 0, x2 equals 0. The null space of that matrix is just the 0 vector. Okay, now let's determine the range. I'll have 1, 2, 1, 3, 7, 5. B1, B2, and B3. All right, and I'm going to row reduce it. This is the same steps. So 3, 1. If I subtract 5 minus 3, that's 2. All right, so B2 minus 2B1. Yeah, subtracting it. This is still B1, and B3 minus B1. And then I'm going to subtract 2 row 1s from row 3. That's going to be 1. Okay, so 1. Okay, so I'm over here, and I know that this has to equal 0. Okay, so the range, and maybe I could simplify this, right? Because this is negative 2b2 plus 4b1, so it's 3b1 minus 2b2 plus b3. I know that has to equal 0, so I'm going to say the range of that matrix is equal to the set of all vectors x, for which 3x1 minus 2x2 plus x3 is equal to 0. And now, finally, that is over. That was a rough set of problems. I thought that, I didn't even think I was actually assigning that much. That was a huge mistake. Okay, exhibit a matrix M so that the range of M is equal to the span of S. Okay, this is good, right? Okay, so the span is, the set of all possible combinations of these vectors. But the range of a matrix is the set of all possible combinations of its columns. So any kind of matrix we make with columns made up of these vectors will be a matrix M with the range of M equals the span of S. So, maybe I'll even write over here. M is equal to negative 2, 1, 3, 2, 2, negative 1, and negative 2, 7, 7. That's a matrix that has the same range as the span of that set. All right. Now exhibit a 1×3 matrix for which W equals the null space of B. I found this one to be a little interesting, so I copied it out of the textbook. I think it would have been more interesting if it was a large, 1 by 3, 1 row by 3 columns. Whatever. All right, B equals, I've been using a lot of uppercase B in this video, so I'm gonna just call it like A1, A2, A3. So that W is equal to the null space of B. All right, well, the null space is the set of all vectors where if I take x1, x2, x3, and I multiply it on the right of A1, A2, A3, I'm going to get 0, right? Because this is set up, it's the inner product. So this is equal to 0. So I've got A1, x1 plus A2, x2 plus A3, x3 equaling 0. But they're telling me that 3x1 minus 4x2 plus 2x3 has to equal 0. So I feel like that's got to be A1, that's got to be A2, and that's got to be A3. I'm just going to exhibit that matrix. 3, negative 4, and 2. Yeah, okay, yeah. Okay, for some reason I thought maybe like 3, negative 4, 2 was going to be a vector in the null space. I don't know why I would have thought that, but that's not sensible. Okay, that's all for this set of problems. This was quite a lot, kind of a lot. But thanks for watching.